Howdy, everyone. Today we will be talking about federated learning with fair worker selection and a multi-round submodular maximization approach. My name is Tural and my teammate is Hoy. So let's get started with the brief introduction. So our background is we know that federated learning is basically used for to get a optimized memory management. And we know that cloud services are now more popular because there are a lot of advancements in AI that helps that with the help of the cloud servicing memory management. So we know that it is pretty much impossible to store data in a single machine, and we have seen a lot of incidents in the past from a data leakage that has caused due to the fact that a lot of data has been stored within one server. But with the introduction of federated learning, now we have much improved system. And because of this improvements, we have better resource allocation, better optimized system, way more efficient server and cloud services, and so on. So we introduced this topic called federated learning, and I will give more detail about it later. But first, let's discover what is the goal of our paper. So, goal of developing such a federated learning system for distributed system starts with a better resource allocation. With these algorithms that we have read from our paper, we ensure safe environment, resource allocation, lower costs within our server systems, and also there are a lot of improvements in the research field with this cutting edge algorithm and analysis. And what do we mean by that? Why this is very useful? This is very useful because we might have a lot of servers within our system and within our data center, and some of these servers are probably not even used for a lot of tasks. Some servers could be more powerful than the other ones, and just because they are more powerful, they get more priority over weaker ones or some of the ones that don't really do much work. Federated learning makes sure that that is not the case, and all of the servers that we have, we optimizely use them, which actually is very better for the cost efficiency, and also it is better for overall performance of these servers. So, what is our motivation in this paper? There are a lot of actually papers that have been published for federated learning, and you can see the examples of it, like a worker selection, federated learning, submodular maximization, and so on. But all of these papers lack one perspective, and that perspective is about fairness. If we do not have fairness within our systems, even though if it's efficiently employed and compiled within our servers, we still not reach the most optimized solution within our servers. So our paper introduces new concept to a federated learning field, which is including fairness. We include fairness, and by including fairness, we also ensure that our solution is most optimized solution within federated learning, and also ensures that we do better than all of those past papers. Now I will pass it to my teammate, and he will introduce more about the federated learning and algorithms.
Hi everyone, my name is Wei. Now I will briefly talk about what is the federated learning. And in this figure, I will explain how does it works. So first of all, the server will assign different tags to the different devices, and these devices have their own data. So these devices will learn their own model by using their own local data. And then the server will collect this model from this device and aggregates them into one single global model. So it sounds familiar like a load balancing in a course. And now the question is, how do we assign this device into several tasks? So it is intuitive that we take all the worker in every training task, but there are some studies shows that actually the global model's accuracy becomes worse because of the sample size increase. That is because every worker or every device have different data size and the capability. So the one way to address this problem is that we are not going to select all the workers. Instead, we only select a subset of the worker for each training task and maximize the average utility of the all tasks. In here, the utility means the performance of the model, like the accuracy. So you can see this figure. Suppose we have 3 training tasks. For the training task 1, we can select worker 1, worker 2, and worker 5. And for the training task 2, we can select worker 1, 2, 4, and 6, and so on. So So our problem will become how do we select a subset of the workers for each training task and to maximize the average utility. So to maximize the average utility, it is possible that some worker may never be chosen. What do we mean by that? For example, in this figure, you can see that the worker 4 is not chosen in the either text 1, text 2, or text 3. And that is because that maybe the worker 4 has the poor performance because of the maybe the different data size or this model will over-represent by the workers with higher computing capability. For this, you can see like this figure, the worker 1 has higher computing capability, so the overall global model can be represented by the worker 1. So to address this problem, we need to ensure that each worker must be selected at least for a certain fraction of the time. So in the federated learning, there are two main problems we need to solve. The first problem is how do we choose a subset of the workers for each training task to maximize the average utility over all tasks. And there are some studies show that it's actually an NP-hard problem, which means it is not solvable in a polynomial time. And the second problem is that how to ensure each worker must be selected at least for a certain fraction of time. And to solve this problem, we add one more constraint on the original problem called the fairness constraint. So our problem will become more difficult because our problem original is the NP-hard problem. So if we add one more constraint, it will be more difficult. So how do we solve this problem? And actually, this paper, the author proposed a solution that we transform the problem into a approximation by multilinear extension, and they also proposed the algorithm that use the greedy algorithm and the randomized rounding to select a subset of the workers to make sure the maximized utility of all tasks and also keep the fairness constraint. And here is the basic concept of the algorithm. There are two steps. The first step is to find a fractional sequence. Here, the fractional sequence means the probability sequence. And in the first step, we will calculate the utility improvement of each worker and then use the greedy algorithm to come up with the fraction sequence. For example, suppose we have 4 workers and we assign the 0 value for each worker. Here, the value means the probability of select the worker. So by doing the first step, we can somehow compute a probability sequence like this. For example, we have a 23% chance to choose the worker 1 and so on. So once we have this probability sequence, we can run randomized P-G rounding for t times to generate our integer sequence. For example, for the task 1, we can choose worker 1, worker 3, and worker 5. And for the task t, we can choose worker 4 and worker 5. So this is the basic concept of the algorithm in the paper. So the next question is how do we come up with the probability sequence from the 0 probability sequence? And now I will give an example to illustrate how to compute the probability sequence in the first step. Now, suppose we have 4 workers with the probability 0.2, 0.4, 0.1, and 0.7. And suppose we know how to compute the expected utility function. Let's suppose the value is 0.6. And now our main problem is how to select the workers to maximize the overall utility. So there are 2 keywords. The first word is how to select the workers and how to maximize the overall utility. So how do we use the greedy algorithm on this? First, we can examine each worker to see how the overall utility improve. And then based on this overall utility, we can select the worker that maximize the overall utility and also keep the fairness constraint. And here is the example. And suppose we already have this probability sequence. And then the next step is if we choose the worker 1, which means if the worker 1 has the probability 1, and then somehow we can compute the expected utility value, for example, like the 0.7. So what is the meaning of these 2 values? It means if we choose the worker 1, the overall utility improve by the 0.1. So the next step is how about we choose worker 2? That means if the worker 2 has the probability of 1, and then the overall expected utility becomes 0.65. So we can say that if we choose the worker 2, the overall utility improved by 0.05. And we can compute the worker 3 and the worker 4. And then we can obtain a sequence W. The sequence W means how the expected utility improved by choosing the workers. So now our greedy strategy is that if we know how the overall utility improve, we need to select the worker based on this W sequence and also keep the fairness constraint. So in order to obtain our optimal solution, which means we need to find a sequence X that maximizes the X transpose times W, and every element in this sequence X is in the range of 0 and 1, also obey the fairness constraint and the continuity constraint. So what is the meaning of this X? This X means the optimal solution for the current probability. So that is the strategy of our greedy strategy. So once we have the optimal solution, we can update our probability Y with the small fraction toward the optimal solution X. So here is the formal expression of the first step. First, we initialize a zero sequence and a variable tau equals to 0. And then we compute a sequence W. In every element in the sequence W, we iterate all the workers by computing the expected utility of the current probability, and we also compute the expected utility of the work if we pick up the worker U, and then we compute the difference between these two values. And once we have this sequence W, we can obtain the current optimal solution, and then we update our probability sequence by a small fraction delta, and also we update the variable tau. And it will repeat the step 2 and the step 4 until tau equals 1. So here is the details of the first step. And then once we have the fraction sequence Y, we will run the randomized rounding t times. What is the randomized rounding? It means basically in this sequence we will pick up two different elements, and the value of these two elements is in the range of 0 and 1. And then we will compute A and B based on this formula. And then we will update the value of these on the step 2 and the step 4 until every value in the sequence equals to 0 or 1. And then we will choose the element that the value equals to 1, and that is how we do the randomized rounding. So here is the summary of the first algorithm. First, we will initialize a zero sequence, and then we will calculate the expected utility improved sequence W, and then use the greedy algorithm until we find a fraction sequence Y of 1. And then we will run randomized rounding for t times to generate the sequence S1, S2, and ST. So here is the basic figure to illustrate how does it work. However, there is a little problem in this algorithm. For example, suppose we have two workers, and the x-axis means the probability of the worker 1, and the y-axis is the probability of the worker 2. So the value is in the range of 0 and 1. And because we need to obey the fairness constraint, so we only can choose the data only in the range of R, and the 1 is the feasible data, which means all the data in this region is feasible. So let's think about the algorithm. In the beginning, we initialize the 0 value. So it is possible that there are some data are not in the feasible region. For example, we can see that the data point Y of tau is not in the feasible region. And because we only update the data by a small fraction, so it is possible that the next step of the data still are not in the feasible region. So in order to solve this problem, the author proposed another solution, another algorithm, which means that we are not going to initialize the sequence from 0. Instead, we initialize the data which the value is the minimum value of the fairness constraint. So by doing so, we can see that all the data in the past are in the feasible region. So basically, the second algorithm is almost the same as the first algorithm, but there are only two differences. The first one is in the initialization, the probability sequence equal to R, and we also modify the update rule. Now can we optimize more? Now I will pass to Taro.
So, as you guys know already, my teammate talked about fair CG1 and fair CG2, and we see that they are very efficient, effective. But as a computer scientist, we always wonder, is this the most optimal solution that we have? Well, of course not. We can always try to do better. But what do we mean by better? We mean that there could be a possibility that we could get much lower complexity within our algorithm. We can get a better fairness constraint within these algorithms. So let's explore the algorithm that we have that helps us to achieve these points. So now we introduce FairDG. What this algorithm does is basically takes the greedy algorithm and greedy approach to another level. And what do we mean by that? So let's say that we have a bunch of workers. Some of the workers are more powerful, they have more capability than the other ones. And our fairness constraint explains that the weaker servers have to be given some kind of priority so that there's a fairness throughout our servers. But how do we approach this challenge with the greedy? Of course, we can start selecting only the workers who are weak. And that means that by selecting the weak ones, we satisfy the fairness right away. So that is what basically our algorithm does. It gives highest priority to unsatisfied workers, which are the kind of workers with the lower capabilities. And then after we select those, we also calculate the value that we will have from the set S after adding those values. So my teammate talked about probability and the improvement. That's what basically means. After adding those weak workers that we have, how does it change our probability and our values? So after this, we introduce something called depth, and depth is a kind of violation of a fairness. So if you violate the fairness, you get a depth. So that's where in the third round, we do that in each iteration, we select a set A that basically only have workers with a non-negative value, which means that the workers do not have any violation of fairness. But here we have two approaches. Obviously, we get a different kind of set sizes. Now we could have a set of workers there are a lot of workers who are weak, or we have a lot of workers who are strong. So then that means that our sizes for set A changes. Depending on the size, we can do two things. The first approach is if we have less than K violated elements, and K violated elements means that unsatisfied workers, we select all of those violated workers, and then we select K minus A elements from the remaining satisfied. That means that, okay, so if we have 3 unsatisfied workers, but we need to maintain 5 workers for our calculations. The rest 2 remaining, we can pick it up from strong workers, so we can complete our set. That's what it basically means. The second approach is, what if we have more than K? What if we don't already have enough unsatisfied workers? Then we basically choose this set based on their depths using more greedy approach. So we see that after making these adjustments, what could happen? We are basically aggressively enforcing fairness, and because in the first round we only choose the ones who are not satisfied, meaning that weak workers, and that ensures us intuitively. You can see that guarantees short-term fairness. That's the first thing we achieve. We achieve the fairness right away. But we also can see that there's a long-term fairness. What we mean by that? Of course, if you iterate these rounds infinite number of times, each worker's depth will go to 0. That means that at some point, every unsatisfied worker will become a satisfied worker, and all of the satisfied worker will also get to work every time infinite number of times, and our depth will go to a 0. But is this a perfect solution? Of course not. And what do we mean by this is not a perfect solution? So there's this weakness that we found in the paper, and paper does not include time average utility. What do we mean by that? So as you know, my teammate previously mentioned about fair CG1 and fair CG2, and basically all of our calculations revolve around maximizing the average utility, also maintaining a fairness. But in this scenario, our algorithm does not even calculate average utility. It only considers the fact that you have a fairness constraint, but you have to satisfy that fairness constraint as soon as possible. So in long term, that in the future, our paper could also extend and explore more about the time average utility while also maintaining a short-term fairness constraint. But we also we will be showing more experiment results, but before showing it, I wanted to give you all a heads up. So our initial problem is an NP-hard problem, and NP-hard problems are very difficult problems to solve, and in fact, we don't really know if we can solve them polynomially or not. So just because they are very difficult problems, we cannot get to the most optimal solution, but what we can is we can get very close to it. Earlier in this presentation, my teammate also introduced about the ratio, and what ratio this means that what is the likelihood and the range of optimal solution that we can get to, how effective our algorithms are and how close we get to the optimal solution. So here are evaluation results. We have 4 charts that are showing you comparisons between FAIR CG1, FAIR CG2, FAIR DG, and also our optimal solution. From the first graph, you can see actually our FAIR DG algorithm gets a better solution than our optimal solution. So it's very, very effective. And you can see the comparison between FAIR CG1 and FAIR CG2 on the charts here, and you can see that they are showing very close results, and our optimal solution is on the top here, which means that our FAIR CG1 and FAIR CG2 results are very, very close to it indeed. And from the other graphs, you can see from the graph B and graph C, in each round, how close our solutions get. So from point 0, we can see that actually our FAIR DG fails to show any worker selection in the T rounds, and also at point 5, worker 5 is not selected for FAIR DG. However, for the results of FAIR CG1 and FAIR CG2, we maintain a very close relationship. As you can see from the chart, they are very close to each other. But there are still a lot of differences between optimal solution. However, the second B graph shows that, as you can see, this is a required selection with the red. Our algorithms do satisfy that requirement pretty easily. And other graphs show how our selection fraction for workers change between FAIR CG1, FAIR CG2, and FAIR DG. And you can see that FAIR DG, even though it starts very good, but it still does not maintain its consistency. But FAIR CG1 and FAIR CG2 maintains its consistency, and they show pretty close results. Following this, what are the summary? What we learned from this evaluation? What we learned is that our algorithms get very close to the optimal value. And in the paper, it even calculates it further and says that within 1% threshold, we get close to the optimal value. All of our algorithms satisfy the fairness, and it shows that our algorithm's approximation ratio gets the best value in the industry, which is 1 minus 1 over E. However, there is one interesting fact in figure 2a. As I mentioned earlier, FAIR DG algorithm, it reaches even better value than optimal value. But even though it does, it violates some fairness for some workers. That is another point that I want to bring it up, which is some weakness in the paper. And it feels like these algorithms are not enough experimented and tested. And it shows that FAIR DG is not really optimized, and it's not really stable. At some point, it shows some better value, but at some point, it fails to live up to the standards. So what are the real-world applications? What are the real-world examples that we can show that federated learning with the fairness could be used to even optimize it and even take it to the next step in the industry? So we have some examples. For example, source scheduling in wireless sensor networks, task assignment in crowdsourcing platforms, data subset selection in the machine learning, and then lastly, the Amazon Payless Store Management, which as a group, we came up with the idea, and we will be showing you how this could be used. So let's explore more about what we mean about our new application. So Amazon has a new store and this new technology where you can walk into the store and you don't even have to pay. You don't have to do anything. There's no cashier, there's no self-checkout. You just pick out whatever you want and you just walk out. There are actually some stores in Seattle, Chicago, London, and New York City. But what do we propose? We propose that Amazon basically uses their camera systems to process data and send information and receipt back to their customers. But also, store could be very big. There could be some location and some popular items that people go pick it up from there, but some unpopular items that people don't really go there. Therefore, even though there are cameras that are set up in every place that processes these customers, some of them might not even get to process anything because there are not many customers going to that location, going to that corner of the stores. So we introduce federated learning with the fairness, and we say that we are very sure that we can guarantee most optimized solution for Amazon stores. What do we mean by that? So let's say there's a one corner, there's a camera that does not get to process any details because there's not many customers going to that location. But in another location, we have overwhelmingly so many customers, and cameras in that corner of the store processes so many customers that it slows down the whole process. By employing federated learning with the fairness, we can ensure that all of those cameras that do not get to process many customers also get some share from highly populated area of the store and highly tasked servers from the store and share it between them. So how do we know if it'll work? Well, this is very close to a concept of task assignment in the crowdsourcing platforms. And in our paper, it actually is proved that federated learning with fairness improves task assignment in crowdsourcing platforms. So our algorithm for Amazon stores would be something very close to this concept, which would increase efficiency within our system and allocate our resources better. And can we prove it? Well, we can prove it because Fair CG1, Fair CG2, or Fair DG actually maintains max average utility. That means that that's the best value you can get. And on top of it, we satisfy the fairness. By satisfying the fairness, we ensure that all of your servers within the store works together and all of them processes some kind of data. Thank you so much.